Okay. So all right, so so we call conjugacy classes equivalence classes, right? So let's make a comment. So the name suggests that, group elements in the same conjugacy classes are somehow, morally equivalent, right? Meaning that they are, in some sense, do the same job. So what does this mean? So, let's just take the case. Let B be a group element. Say let B, it doesn't have to be a reflection, but you can keep that in mind if you want. Let B be a group element, and say V is a position vector. From the center of the shape, it could be a triangle. So for example, let this be V. Okay, so this is some vector V. And now, suppose we make some transformation on V, and which is by B. So B takes us from V to something else. Okay, so this is, say, this is a transform vector, say V prime, and this is B acting on V. So you could say that, okay, B is a reflection, or it could be a rotation, say, to an angle, say, theta. Okay. So now let alpha be, so let alpha be a, say, a rotation or another transformation. Now acting on, say, V. So alpha takes, say, suppose it takes this V to something else. Let me see if I can. Sorry. So suppose that alpha takes it to this, okay? So this is going to be a new vector, which I'm going to call, say, alpha V. Now, the question is, what is a transformation that will rotate alpha V by an angle theta? Okay, so that is basically what the conjugacy class, answers. So essentially, what is the transformation such that this angle is theta? So that will have to. So this transformation will act on this vector, right? So this transformation will act on this vector, and that transformation we know that it was B over here, but in this quote unquote rotated frame is going to be given by alpha B alpha inverse. Okay? Which of course, if you simplify it, what do you get? You get alpha, you get B, V, right? So which is essentially this vector rotated by alpha, right? So this is a geometrical interpretation of a conjugacy class in general. Okay. Is there any questions?
So could you repeat the explanation of alpha B V and just BV?
Right. So let's take those pictures again. So suppose that we have some vector, say V, and we do some transformation on the vector by B. We say involves rotating it by some angle theta, right? Or it could be a reflection. It could be some general transformation. But for definiteness, I'm taking it B to be a rotation by theta. Now, suppose that I rotated alpha by some other angle, by denoted by this group element alpha. Now, my question is, what group element will now act on this to give me a rotated vector by theta? So previously, we saw that to rotate V to V prime, we had to act by B, right? But now we are talking about a rotated vector, a vector rotated by alpha. So the group element that's going to rotate this guy by the angle theta is going to be then alpha B alpha inverse.
So will the second rotation be on right side? I mean, clockwise?
No. No, because here we are not talking about reflection, B being a reflection. Okay. Here we are talking about B being a rotation.
Sir, I had a question.
Yeah.
So like B is kind of a phase in this case, if B is like a complex number. So like why would B change if we like rotate the frame? Isn't the phase angle the same still? I mean, like why would the transformation change? I mean.
Well, in that case, you're thinking of something where you're thinking of a case where it's an abelian group, right?
Oh yes.
So in that, yeah. So these are more general. So coming back to Farhan's question, you can think of it as being, say, B being some transformation that reflects around this axis, right? And B being that transformation that reflects around this axis. The new alpha inverse, that if Farhan, if you want to think of B being a reflection, then what it's saying is that the new axis of reflection should be this one. Okay.
So we have the V vector, and applying B, we get BV. So that's theta degree shift. And after that, we multiply with alpha. That's again a theta degree shift. Is that the case?
Yeah, I mean, I think it's best one way of thinking about it. So this is a geometrical way of thinking about it, but there's an algebraic way of thinking about it. The algebraic way is that suppose you have some matrix, right? The matrix is some general linear transformation. Suppose it acts on V and gives you some other vector, say W, right? Now suppose that you have changed your basis, right, in such a way that you have rotated this vector V. So you have applied a rotation on this vector V, and you have found a new vector V prime, right? So but M acting on V gave you some W, and say V and W is this is going to be some angle, right? If you divide by, say, their mods, right? This is going to be this captures the relationship between, you know, V and W. So you want to find a W prime such that, you know, V prime W prime and, you know, say V prime W prime mod is equal to V dot W, right? So I'm going to ask you, you know, what is going to be the, you know, how can you go from V prime to, say, W prime, right? And the answer to that would be that you basically have some matrix M prime, which is R M, R inverse, and that matrix M prime acting on, say, V prime is going to give you W prime. So in a sense, you know, these equations and this equation and this equation, they are equivalent equation, but in a different basis, right?
Yes, sir.
So this is the action, this is the group action. And that group action in the rotated basis takes you to an analogous group action M prime, which is related to the original one by a conjugate, by a conjugate action, which in matrix language is called the similarity transformation, right? Okay. So, so this is basically the algebraic way of thinking about it, is that somehow you're changing the basis in which, this is not the most abstract way of thinking of it, but yeah, okay.
Okay, sir, got it.
Okay, I mean, I think, you know, these ideas will become clearer as we progress, because we'll be cycling back and doing more examples, say when we do rotation. So, but you know, I'm still, you know, happy to talk about this if people have questions. Okay, we have some comments. Let me in the chat. Okay, now he's saying that thanks for the insight. This clarifies the geometric interpretation of the conjugacy classes. Otun has said BA squared are their own inverses, since all three of them represent reflection. Yeah. Okay. Very good. Okay, so let me make some comments on the dihedral group before moving on to the next group. Comment number one is that in abstract algebra, Dn is known as D2n, okay? Because there, you know, this index is referring to the number of elements or the order of the group, whereas in geometry, it's referring to the number of sides of the object whose symmetry group Dn is. Okay. Now I want to give you an exercise, one of those you know, blue exercises in a red box. There'll be quite a few today, and hard ones too, because I'm lazy. No, I'm just kidding. I think it's good for you to do this. Okay, so show that show the following: the centers of Dn. Oh, I should really not use red. should be a red box. Okay. Okay, the center of Dn, depends on whether n is odd or even. Okay, so if n is odd, then we can say n is, say, 2k plus 1, where k is a positive integer. Then show that the center of D, 2k plus 1, is just the identity. Okay. But if n is even, if it's 2k, then show that z of D of 2k is the identity and the rotation raised to the power k, and that this is actually nothing but the Z2 group. Okay, so this is an interesting exercise, and let me just box it up. My box is not working.